All right. Well, welcome everyone to today's session. Okay, so we're gonna cover a variety of topics today. I'm gonna be the first leg of this race, and we'll be talking about the thermodynamics. In particular, we're gonna focus on the convex Hall analysis for stability. And then Dr. Friedrich is gonna pick up in the next session with addressing a very important error within DFT for polar materials. And then I'll pick it up after the big break in the middle, and we'll talk about the sort of materials. So today's topics, they're going to be directly related with a lot of Professor Kuderolo's keynote speech. So if you're interested in those topics, today's the day to sort of get more in detail with those analysis. All right, so let's get started. Okay. So the question for today's lecture that you should keep at the forefront of your mind is the question of whether a material will form. Okay, so there's two domains within which we can ask this question. Both domains are important questions, and they both need to be resolved for really understanding whether materials are formed. But there is the kinetic domain, and then there's the thermodynamic domain. Okay, so here we have a plot of a reaction. We have two reactants. You see here that we have a pure phase of blue atoms, and then we have a pure phase of white atoms here. And we can follow the energetics of the reaction. Okay, so there's a transition state in the middle here. And then we see the energy of the products. Okay, so we can get various forms of the mixture here. You can see that we get one variety here, and we get another variety here. And we want to understand if we take the pure blue atoms on one side and we mix it with the pure substance of white atoms on the other side, we mix it together. Are we going to form product one or product two? Okay. So if we're interested, if we look at the kinetic domain or the kinetic control, we're going to be, so we understand that the reaction is occurring at some sort of temperature. So there's an energy that under which that the reaction is occurring. Above this energy, the reactants cannot reach because there's not enough energy in the system. So if we follow kinetically what the reaction should be doing, we see that the pathway for product one, there's enough energy for the reaction to follow through its transition state where there's a higher energy state that's realized, and then we can realize product one. Product two virtually will not form because the energetics of the transition state are too high. So this is the result of what we would get if we're looking under kinetic control. If we focus purely on the thermodynamics, then we look at the beginning state and the end product. We don't look in the middle. Okay, so you can imagine that we sort of blur out the middle here. We just really focus on the end product, and we see that the energetics of product two are lower than product one. So if we look at it from a thermodynamic perspective, this is what we expect to see. Okay, so again, we need to look at both controls to really understand the full picture of the reaction here. But for this talk, we're going to focus primarily on the thermodynamic domain, and we're going to really just focus on what the beginning substances are and what the final reaction is, what the products are, and we're going to ignore the transition states in the middle. We want to ask the question whether a mixture is thermodynamically stable. We want to understand whether this mixture is going to decompose into its components. Okay, so this mixture here can decompose into pure component A and pure component B. In this case, I give them labels. So our mixture here is palladium, platinum. And we want to understand, is it going to decompose into pure palladium and pure platinum? This is like asking the question, is the oil and vinegar going to mix in our salad dressing, right? If we mix it long enough, if we mix it, it's going to mix, but then it's going to phase separate, okay? So this question is really a question of energetics, right, from a thermodynamic perspective. We want to understand, are the energetics of this reaction favorable for the decomposition? So this G here, this is our thermodynamic potential of interest. This G is the Gibbs energy. It depends on the temperature, pressure, and the stoichiometry, the compositions of the mixture. There are other thermodynamic potentials of interest, but these are the parameters that we can control very well with an experiment. Okay, we're really concerned about temperature, pressure, and the composition of the components here. So we have two terms of interest here. We have the enthalpy term here, and then we have the entropy term here, which is scaled by the temperature. Roughly speaking, you can think of this as the ordering in the system and then the disorder in the system, and they compete for stability of the material. So we know that stability here from thermodynamics is really a question of where we minimize the energy, and a corollary to that is that we want to minimize the energy or maximize the entropy. Okay, so those are sort of two equal parts of the question here when we're asking the question of whether we're in equilibrium. For this talk, we're going to focus really on the enthalpy term. We're going to focus on the ordering term here. Now, in the later sessions, we're really going to hone in on the disorder term. But for this part, for the convex Hall analysis, we're just going to focus on the enthalpy term. Well, how do we calculate the enthalpy of material? Well, enthalpy is the internal energy minus the negative of the pressure volume term. We're going to ignore pressure volume term. It's going to be important because we're ignoring temperature, pressure, because we're doing density functional theory calculations, and these are really ground state calculations. So, we can do our calculations at particular pressures. We can do them at particular temperatures, but the majority of the base is really constructed with density functional theory calculations, which were performed at zero pressure, zero temperature. Okay, so let's focus in on this term here, the internal energy. We look at the internal energy of a mixture here. We can break this up in sort of a Taylor expansion sort of series here. So if we look at the first term here, we know that every atom carries its own energy. Okay, so we can look at the energy of the blue atoms and the energy of the white of the blue atoms and the white atoms. They each carry their own energetics. We can look at the bonding. Okay, so how are blue and white atoms bonded respectively? Are they bonded to blue and white? Are they going to be bonded? Are the blue and blue atoms going to be bonded? Are the white and white atoms going to be bonded? What is their configuration of interest? And we can look at nearest neighbors, next nearest neighbors, and so on and so forth. So this is what this term carries. We can also look at bonding with several atoms. Okay, so we can look at bonding between three atoms here. Okay, so we get additional terms like the angle between the bond, angle bending and bond stretching. These sort of terms come into play when you're looking at these third order effects, and so on and so forth. So, okay, so for the discussion here, the important part is that we're going to get the internal energy from density functional theory. So this comes from our first talk where we talked about leveraging VASP. We're going to understand the enthalpy of this system from a quantum mechanics perspective. So we want to understand what the energetics of the electronic density are. But for this talk here, we're really just going to treat it like a black box. So we take our system, we have some sort of configuration. So we have a geometry file. We're going to have some pseudopotentials, some input settings. We take that system, that calculation, we run it, and we're going to get an energy for this system, and then which is going to be the enthalpy, because we don't have any pressure or temperature in that calculation. Okay, so we can run VASP for our three systems here. So for the mixture and for the pure components, and we're going to get an enthalpy for each of these three. And we can look at the enthalpy differences from one side of the equation to the other side of the equation. We can balance that. For this talk, we're going to be focusing on a particular variant of the enthalpy, which is called the enthalpy of formation. Okay, so what we do here is that So we're going to be focusing on the enthalpy of formation, which is the question, which is really the enthalpy of the system after you've subtracted off the enthalpies of the pure components. Okay, so what we're doing here is that, see, we have an enthalpy for the mixture and then enthalpy for the pure components. We're going to zero out, we're going to subtract off from both sides of the equation the enthalpies of the pure components, and we're going to get a new enthalpy for the mixture, which is the enthalpy of the mixture minus the stoichiometric weighted enthalpies of the pure components. Okay, and in a minute, it's going to become very clear why this is important. Okay, so we're gonna visualize the energetics of this reaction. So on the y-axis here, we have the formation enthalpy, okay, the energetics of the system. And then on the x-axis, we have our stoichiometry range. Okay, so we on the zero here, you can look at this is like the zero line here. We have pure palladium. And then as we go to the other extreme, we have pure platinum. And in the middle, we can have a 50-50 mix. We can have the whole range in the middle. So here I have plotted with X's where the three materials are energetically. So here we have pure A, here we have pure B, and then we have the mixture here, the 50-50 mixture. And so by plotting with respect to the formation enthalpy, what we've done is that we've zeroed out the enthalpies of the pure components so that they sit right on the zero axis here. Okay. And now what we want to understand from the reaction perspective is we want to understand whether the energy of this mixture here, this blue X here, if it's lower than the tie line connecting the pure components. Okay, so that is really the question we were asking earlier about this decomposition reaction. So you can see here from this picture, the mixture is lower than this green tie line. Okay, visually you can see that it's lower. So that tells us that the mixture is stable with respect to decomposition into its pure components. Okay, so we get a gain in the enthalpy by going from the pure components to this mixture. Now, this is a question that we need to ask not only for the pure components, but we need to ask for all different types of mixtures that can exist in nature. So what I have here is a picture of all of the enthalpies for different configurations and different mixtures, different ratios of blue to white atoms that come from the AFLOW database. So you see here that I have a system here which is more palladium than platinum. So I'm going to have more blue atoms than white atoms. Here I have two different configurations of the 50-50 mixture. You see here that I have this nice tiling here and this mixture here. And then I have another configuration which has equal parts blue and white, but the arrangement of the atoms is different. So that's going to give me a different energy. And then on this side, I have more white atoms than blue atoms. Okay. So we need to look at the possible decompositions with all of these different configurations, whether we change the arrangement of the atoms and we change the ratio of blue and white atoms. So visually, we're going to be building all of these different tie lines and looking for the most stable configurations. Okay. And this question of which systems form the most stable configurations, the most stable configurations in the system, most stable states. This is a question of what is the convex Hall for our system here. Hold on. Okay, what is the convex Hall for our system here? This is the convex Hall is really a general, it's a concept that we borrow from mathematics. You can do this for any data set. And the convex Hall visually is actually it's very simple. Imagine taking a giant rubber band and wrapping it around the data here. Okay, one second. I see that there's a question. Let me see what the question is. For more than two species, will our references still be the elements? Yes, that's a great question. The enthalpy of formation is always defined with respect to the pure components. That's the enthalpy of formation. You can look at the enthalpy of mixing, which can be the enthalpy difference between the, let's say, the experimental precursors, which may not necessarily be elements. Okay, so but from the perspective of our analysis here, the formation enthalpy is always defined with respect to the pure components. That's a great question. Okay, so getting back to it. So imagine taking a giant rubber band, wrapping it around the data. The points that touch that rubber band, those are the most stable points in the data set. Okay, these are the compositions which do not decompose into any other linear combination of states in this system, in this ensemble. Okay, so what are the various components here of the convex? So here we have the tie line. The tie line represents two-phase equilibria. Okay, so what it means is that if I take these two components and I try to mix them together, they're going to happily coexist phase separated. Okay, so they're not going to want to mix. They're just going to stay phase separated if I'm along this tie line. If I'm off the convex hull, right? So the convex hull always comes from the bottom. So if I'm above the convex hull, energetically speaking, then all of these systems here are unstable, and they're going to destabilize to a linear combination of the phases on the tie line below it. So if I want to ask the question, what is the decomposition reaction for this system here? What I do is I draw a line directly down to the facet directly below it, and that defines my decomposition reaction. So here I have this PD2 PT3, and it's going to phase separate into PDPT and PDPT3, and I can balance that equation just by balancing the respective compositions here, and I've done that below here. So visually speaking, just taking my point, dropping my eye to the facet below it, that tells me the decomposition. But that distance is also an important metric, that energetic distance from the point to that vertical distance from the point to the facet below it. That also tells me the decomposition energy reaction. So what is the driving force for this reaction? You can imagine that if this distance is very large, then the products are going to be heavily favored over the reactants. So it's really going to want to decompose. In this case, the distance is very small. It's 3 MeV per atom, where small here is the thermal excitations at room temperature, right? So if I take the Boltzmann constant multiplied by room temperature, I get this sort of magic number from statistical mechanics, which is 25 MeV. So practically speaking, if we're looking at all the points that are within about 25 MeV per atom, then that distance is pretty small. And this is an important metric, because you have to remember that our picture here was constructed at 0 temperature, because that's the nature of our calculations. So if we introduce temperature into this system, if we introduce pressure into the system, this picture is going to change, and the points that are going to be the most stable they may be different. So the question of how this picture looks like at room temperature, you can imagine error bars which are of the order of 25 MeV per atom. Okay, I see another question. Are vibrational, rotational, and translational contributions included? The answer to that is no. Well, hold on. No, they're not. Vibration is not for certain, but remember, we're analyzing the internal energy of the system, so the configuration is included. But no, to the answer to your question, vibrations, rotations, and translations are not included. These thermal contributions are not included in these calculations. To incorporate this data, we're going to have talks later today. I don't know when they are. I think that they're going to be tomorrow and Friday. We're going to have talks on the AFLOW Gibbs library and the AFLOW Elastic library. These analyses, which you can do with using AFLOW, you can actually incorporate vibrational contributions into your calculation. That is one level of theory. And if you, that's it, that's within the Debye, the Debye approximation. If you want to go to the phonon level of theory, you can also do that analysis with AFLOW. And I believe that Mark was going to be covering that. So Dr. Dresser is going to be covering that on Friday. So that's where that's how you incorporate those contributions. Maybe this is too far-fetched, but can we somehow correlate the distance to the convex hull with the possible microstructure? So the distance, I'm not sure what metric you're alluding to, but yes, roughly speaking, this distance, if it's very small, then it's okay. So these systems are fundamentally metastable systems if you can achieve them in experiment. Okay. So it's possible that that you can actually sort of quench a system which is metastable and have it be realized in experiment. And so if you want to understand how does the experimental picture correlate with the picture that we have here, you can correlate that, roughly speaking, with this distance. So if the distance is very large, you wouldn't really expect that system to form unless there's a lot of disorder, and disorder is driving the stabilization of that material, which we're going to cover in the later session. But from the ordering perspective, remember that there's two components to this Gibbs free energy. There's the ordering perspective, and then there's the disorder perspective. We're ignoring the disorder for this talk. If the system is being stabilized purely by the ordering by the configuration, by the ordering of the crystal structure, then this system would not form because the energetics it's off the hull. It's not a stable system with respect to that ordering component of the Gibbs free energy. Okay.
Or if you don't mind, an additional comment to the three contributions that Raphael was mentioning. Rotational and translational contributions are more important to molecules, especially for a crystal. Translation is not relevant because there's a translational invariance for crystalline solids. And you will see, especially on Friday, that the vibrational contributions, calculating those are not cheap. They're really expensive because they involve large cells, and you'll see, especially on Friday when I talk about phonons, why they're so expensive.
Yes, fundamentally there is a big barrier, and that is cost of the calculation. So to expand on the point, you can imagine that each one of these points here represents one density functional theory calculation. If we want to do if we want to understand the vibrations of each of these points, each one of these involves something of the order of 20 DFT calculations, and it could be more. Okay, it depends on the symmetry of the structure, but you're thinking of tens of DFT calculations. So it's a very expensive calculation, and reducing the expense of that calculation is something that Dr. Heusler is going to go over in quite a lot of detail on Friday. Okay. So some technical details. Okay, so this analysis has been incorporated and implemented in AFLOW. It's called the AFLOW Convex Hall module or AFLOW-CHULL. And I just want to include some technical details here that are going to be important. Because we are doing these analysis from a high throughput perspective, where we've automated the analysis, and we're doing it for hundreds of thousands of different systems, right? If you can take all of the binary, all of the 2 elements in the periodic table, if you take all the 3 elements, you can do all of these convex Hall analyses. So we're doing hundreds of thousands of convex Hall analyses. Humans are not going to go through every single one of them. So it's important that we develop some heuristics for convergence and for convergence of our properties here. So you can imagine that there might exist convex halls where you have outliers. Okay, so why might an outlier exist? Well, an outlier might exist because in general, the calculation is not well converged. Now we have several convergence criteria for AFLOW, so that scenario doesn't happen really at all. We filtered out for that scenario, largely speaking, in our database. Another reason why you might have an outlier is because you might have run the system with different input parameters. Okay, so if you run it with depending on the K point mesh, and if you have a really coarse mesh, maybe these are all calculated with a really coarse mesh, and this is calculated with a really fine mesh, you might have a scenario like that exists. Not in our database, our parameters are really well standardized, but these are different scenarios where you might have an outlier that approaches. If the data you're constructing your convex hull with has outliers, well, we automatically detect them and remove them. Okay, we use the interquartile range to define what an outlier is, and we can remove that and then get the convex hull for our system here. Another problem that exists, and this is a problem that exists in our database because we pull data from the ICSD, and the ICSD does have duplicate data. We want to understand what are the degenerate configurations, right? So each of these configurations might have slightly different energetics, because they're slightly different, but they're really the same structure, but maybe the atoms are slightly perturbed depending on how it's reported in the literature. So you might get different energetics for these systems, and that's going to confuse our analysis, right? So one might look like it's on the convex hull, the others might look quote unquote metastable when they're really just all degenerate. So it's very important from an analysis perspective to identify the degenerate structures. And we use the Xtel Finder algorithm that that Dr. Hicks discussed yesterday. We use this analysis for the stable points, and we can identify which structures are degenerate. And you can see here that for this particular configuration, we know which one is sort of the lowest energy one. So that's the one that defines the convex hull. And then the others are all degenerate. They're all duplicate entries. And so we have an understanding of these duplicate energies, and we just associate all those points together as being right on top of each other and defining that point on the convex hull. Okay, so well, before I get to moving toward the exercises, I've been doing this analysis and showing you the results for two component systems, but we can do this analysis with 3 components, 4 components, and so on and so forth. This is an illustration of what looks like in 3D. So having 3 different components. Here we have manganese, palladium, platinum. And so you can see here that we get this nice triangle shape, and we can look at what the points are. What are the stable points? Here you can see an illustration of the depth of the convex hull. We're gonna look at this online, and I'm gonna show you what it looks like when we add a 3rd component, what this picture looks like. We get a 3D picture. Instead of having tie lines, we're gonna have tie surfaces. So this is an illustration of that 3D convex hull, where the blue here shows us depth. The blue and the orange shows us depth. And so, well, let me stop sharing here. And we're going to go online to our web module where we're going to, we're really going to visualize and understand how to generalize this convex hull analysis to more dimensions. Okay. All right, so let me share my full screen. Okay. You should see my full screen here. Let me open up the chat. Okay, can everyone see my screen here where I have the 2 panels? Yeah, perfect. Great. Thanks for the thumbs up. Okay, so what we're going to do is we're going to navigate to aflow.org, and I'm actually going to expand this, make this really big so everyone can see. Okay, we're going to scroll down. We're going to go to the AFLOW-CHULL module. Okay, so you should see a periodic table and a place where you can type in your elements. We're going to navigate to a nice example, which is silver, gold, and cadmium. Okay, so you can just type that in, hit submit. All right, I'm going to give everyone a few seconds to catch up. Okay, so everybody should be now on the web page here with this convex hull. And what you see here is a very nice visualization of this convex hull. So previously, we were looking at just two-dimensional convex hulls, which you actually have. You have three of them here. So here we have the convex hull for silver and cadmium, silver and gold and cadmium. Okay. So you can actually look at that convex hull, and that's part of this picture here. Okay, so you can look at that analysis. You should be able to zoom in. So you can see that the 2D hulls are part of this bigger picture here of the 3D convex hull. So if we take the if we take the combinations of these three convex hulls, and we incorporate data of also the mixtures of all these three systems, then now we have the full picture here. So you should be able to zoom in and look around. Okay, zoom in, and you might maybe even accidentally click on one of the points here. And so you can see here that decompositions, they might now include three components. So this system here is going to phase separate into these 3 points here. And we can see that visualized very nicely here. So this point here is going to decompose into these 3 points here. And then you can also see that there exist examples where the phase decomposition is still two-dimensional. Okay, so it's going to phase decompose into the pure component here and then this phase here. So you have now many different ways of phase separate. You can phase separate into 2 components, into 3 components, and as you include more and more components, the number of ways you can decompose grows. There's a question here. So CHULL is always calculating based on recent data. This is an expensive API call. Well, it's a great question. Yes, there are. You can actually make the convex hull analysis can do it in a number of ways. You can call each individual entry, and the code. You can actually run this analysis on your laptop. I'm going to show you how to do that in a few minutes, but you can run this analysis from your laptop, and basically it's going to be making this API call, grabbing the respective stoichiometric data, the respective energetic data, the enthalpy data, and building the convex hull right there in your laptop. It's something that you can do on your laptop. You don't need a supercomputer to do so. There is a nice way of grabbing this data using another API, which is called AFLOW. This is our search API, and we're going to be talking about this more extensively tomorrow. So this data question of using the API, this data is gonna, this is very important, and it's gonna be explained more thoroughly tomorrow. But this API call is going to reduce the expense with which you need to the expense for grabbing this data, right? So we'll answer that question more thoroughly tomorrow. Okay. Oh, actually, let me select one of these points because I wanted to show you something about the hull here. Let me reset here. So if I select this point here and I click on it and I wait a few seconds, it's going to make an API call, and it's going to grab the data for this entry. And so we see that we get a little card, a little snapshot of the data for this system. We get the prototype, the lattice space group, the energy, formation enthalpy. We get some of the data from the convex hull analysis. We can see the distance to the hull. If this were a stable point, we might see a stability criterion and an n+1 enthalpy gain. I haven't explained that yet. I'll do so in a few slides, in a few minutes. If you click on more information, you'll get the entry page for our material here. So this is kind of think of this as the Facebook profile for our material here. We get the profile picture here of the material, and then we get all the different properties. Okay, so you have the unit cell, you get the structural data, you get there's a lot of structural data. You can get the thermodynamic properties, the chemistry properties. Everything is really specified here. This is the full breakdown of the material here. Okay, so we're going to go back to our window here, and we're going to select selected hull here at the top. Oh, I got another question. Is it possible to plot in function of chemical potential? Well, the chemical potential is the energy of the pure components here. So that is the chemical potential we're talking about here. So these are the chemical potentials for for the system. The chemical potential is actually, roughly speaking, related to the derivatives of these facets. But I'm not quite sure I understand your question with respect to chemical potential, because chemical potential, that's really the energy of the pure components here. I don't know if you want to unmute and elaborate a little more. Yeah, okay. Okay. I think I've explained that. So okay. So if you click on download PDF, in a few seconds, you're gonna get you should get a request to open up a file that got downloaded. And you'll see that it's going to download a report of the full analysis here. So we get a nice visualization, because this is in 2 dimensions, and in 3 dimensions we can visualize it. 4 dimensions you can actually visualize, but without the you'll have the missing axis here of the enthalpy of formation. You're just going to have 4 dimensions in the stoichiometric axes there. But after 4 dimensions, you cannot visualize the convex hull. You can only visualize projections of it. So for 2 and 3D, we have visualizations here of the convex hull. If you scroll down, you're going to see that there's a very long report which gives you the full breakdown of all of the calculations we use to build this convex hull. And it's organized by composition. So everything that has this composition is going to be in this table here, in these tables here. And every one of these lines represents a different calculation. And it's organized by ternaries. Ternaries are at the top, the highest dimensional data. Then we have binaries, if you scroll down, and then unaries at the bottom. But for every single entry and every single stoichiometric group here, we have a declaration of whether that composition is stable or unstable. You can see that this set of points are unstable. That whole group of points is unstable with respect to the convex hull. This one is stable, so you see that it's written ground state here. For this entry here, we can click here, and that's actually going to bring us to the entry page for that material. I'm going to go back. And then we get some additional data. We have the AUID, the space group before and after relaxation. We have the spin. We have the enthalpy of formation. We have the entropic temperature. We're not going to go over that, but that was an important descriptor that we use for understanding. It's for understanding the enthalpy and the entropy, balancing the enthalpy and the entropy of the system with the ideal entropy. So this is a descriptor that we developed, and it's included in some of our publications. If you want to know more, you can go to this publication here. And then this parameter here, this is the distance to the hull. Okay. So you can see here that it's 162 MeV per atom. So it's very large with respect to that 25 MeV parameter that we discussed earlier. For stable points, we get the stability criterion written here, and we get the n+1 enthalpy gain written here. Again, I haven't gone over that. I'll go over it in a few slides, but these are 2 descriptors that we developed for stable ground state systems. Here we see that the system that really is the lowest energy system that defines the convex hull, that is highlighted in green here. And then in orange, we have highlighted structures which have similar relaxed, which have the same relaxed space group. So these structures might be similar. They are similar structurally, so they might be of interest to look at. One thing I want to highlight is that if you have duplicate entries, you might see more than one entry highlighted in green, because these 2 are duplicates, and we've done that analysis, the Xtal finder analysis, to understand that. Finally, we have a big list here of the vertex of the facets. So if we're looking at any particular point here in the convex hull, what that list gives us are the edges of all the triangles that touch that point. So here's one list of configurations that define this facet here. This is another triangle that touches that point. This is another triangle. As you can see how you can get all those different facets. These are 3-phase equilibria. Okay, and that's going to be important in the next part of the talk that I'm going to give actually right now. So okay, this is all the data you can get from the convex hull analysis. let's go back to our slides. And I'll talk about what the stability criterion and the N+1 and energy gain, enthalpy gain is important. So can you guys see my slides now? Thumbs up if you can.
Yes.
Perfect. Okay, so why is it going to be of use or of interest to understand what these three-phase equilibria are? Let's relate this back to the material science. So we've done an analysis for superalloys. Superalloys are one type of material that we've looked at. Cormac actually, or Dr. Tower actually talked about this in his introduction slide. He showed a nice picture of the turbine blades. Superalloys are very important for extreme temperature environments. Okay, so one of the properties that these superalloys might have is they're going to be very hard. And so one of the ways that superalloys can achieve this hardness is what's called an age hardening process. This is a thermal treatment that is applied to the material that results in the creation of precipitates in the material they're different phase, and these precipitates are going to block the movement of atoms. They're not going to allow for sliding of movements, and so that's going to block plastic flow of the material, and that's going to actually create a harder material. So this age hardening process, this is a thermal process. Here I show in the phase diagrams what this process looks like. You might heat up the material to a high temperature, then you quench it, and then you heat it up again to a slightly lower temperature and you anneal it. And that annealing, that quenching versus annealing is going to result in the creation of these precipitates. Okay, so if we're looking for interesting compositions for analysis to see if they can form superalloys, one question that's going to be important is whether the precipitate and the host matrix can be in two-phase equilibrium with each other. So we were looking at a bunch of compositions that sat on this red line, okay? And we want to understand if a composition on this red line can be in two-phase equilibrium with the host matrix, which is this composition here. So if you have in a particular phase diagram, if you have a tie line right here, then you know that this composition will not be in two-phase equilibrium with this composition, because this two-phase equilibrium is going to block that two-phase equilibrium from existing. However, if you have a tie line that looks like this, well, there might exist a range of compositions where you can have that tie line exist. So those are going to be compositions of interest. That's an example of why you might want to have this information of the two-phase or three-phase equilibria for analyzing or reducing and filtering down compositions of interest. Okay, so that's the two and three phase equilibrium. Oh, I see that there's a question here. Seems you picked the A12 for reference energy over the more stable 320 for manganese. Is there a reason for this? This is a good question. I don't know off the top of my head specifically why we picked this particular reference, but there are good reasons why we pick. We've made deliberate choices in why we picked which reference phase is going to be the one that defines the reference energy for the formation and energies. So for manganese, I'd have to look it up, and we can discuss this offline. I'd have to take a look, but we have made deliberate choices, and some of these choices are going to depend on the particular pseudopotential that you're using. Whether you're incorporating a meta GGA, if you're going to be incorporating additional constraints like that, that's going to change which reference you have. So it's a great question, but let's take that offline because I'm not actually sure how to answer that at this moment. Okay, so for the stability criterion, if we want to understand, so we can build this convex hull. We have an understanding that this convex hull has been built at 0 temperature and 0 pressure. We want to ask the question, how stable are the stable points on this hull? It's possible that there exists a phase which has not been analyzed in the AFLOW database, which if we perform the calculation, add it to the database and plot its energy, it might sit somewhere over here, offsetting this point here. Okay, so we want to ask the question, what is sort of the likelihood of that happening? You can imagine that. Well, let me tell you what the analysis is here. For the stability criterion, what we do for each stable point on the convex hull, we take this point, we remove it from the convex hull, recalculate the new convex hull. So this is the convex hull in the dotted lines that forms if you remove this point here, and we look at the energy difference between the point and that pseudo hull. If you can imagine that, if that distance is very large, it's going to be unlikely that there exists a new phase that's going to, it's going to be less likely that a new phase is going to be much, much lower and destabilize. It's possible that that new phase might sit somewhere in that big distance region. So that question of how likely is it that there exists some new phase, this is captured by this stability criterion. And you can see here that the stability criterion is 6 MeV per atom, which is not very large. We used this stability criterion in identifying a new magnetic phase. So we did a study where we looked at Hoister alloys. We actually looked at these Hoister alloys yesterday, this prototype. If you remember this T001 and T002 and T003, these are different Hoister alloys. We have the regular Hoister, we have the inverse Heusler, and then the half Heusler here. And they're part of a bigger Heusler class structure. So if we take these different prototypes, these 3 different prototypes, we decorate them with 51 different elements, we get a very big list of candidates. And so one of the ways that we reduce down the set to the set of that we're most interested in, we use the stability criterion. So we asked the question, are these phases stable? Is that stability criterion greater than 30 MeV per atom, right? 30 being greater than the 25 MeV per atom, that cutoff that I talked about earlier, the thermal excitations. So if that distance was larger than 30 MeV, then we selected those compositions for further analysis. So of those systems that we filtered down based on various criteria, including the stability criterion, we had 4 systems of interest and 2 were experimentally validated. And I show the experimental data here for one of those systems, which is ferromagnetic as we predicted. And we're actually able to predict very well what the Curie temperature is, which is about 950 Kelvin. And it did form in this Heusler structure that we predicted that it would. So this was a nice validation of this stability criterion that I talked about. Finally, I'm going to talk about the n+1 enthalpy gain more in the disordered system, the disordered talk that I'm going to give a little later today. But one of the intuition we get from this n+1 energy gain that's actually very important is it's this question of recursive stability. So here's the picture we had earlier. We have the pure phases here at the top, defined at the 0 tie line. We have the mixture here at the bottom. And so I said that stability was that this mixture is more stable because you know that it's lower in energy than the tie line. So another way of phrasing this is that there is an enthalpy gained from going from the pure components here, that are made up of only one element. There's an enthalpy gain from going from 1 element mixtures to 2 element mixtures. Okay, so that enthalpy gain is defined from going from 2 dimensions to 1, and that's how we write this notation here. Okay, so we can do this analysis for all of the different combinations of A and B in the periodic table. We can also do this for all the ternary elements. The question now is there an enthalpy gain from going from 3 components to the convex hull defined by the pure components and the endpoints here? Okay, so if I build the convex hull, which is only defined by the edges, the edges of the convex hull, then this ternary system here has an enthalpy gain with respect to convex hull. We can do that analysis. Professor Kuderola showed this picture in his talk. And so what you see here is that if we do this analysis for 2 dimensions, 3 dimensions, 4 dimensions, what do you see? Well, you see that the enthalpy gain decreases. So here we have a histogram of all the possible enthalpy gains that we can get for our systems. We see that the enthalpy gain decreases with increasing dimensionality, and that there are fewer systems that show any enthalpy gain. Okay, and so so the reason for this is that you have to remember that we have recursive stability. So the ternary phase diagram is composed of the three two-dimensional convex halls here. So we have the stable points here of all the binaries here on this plot here for AB. We have the same for BC and AC. So the depth of this convex hall here defines the absolute minimum for the ternaries to compete within themselves. So any ternary that has any lower energy than that defined by the binaries is automatically not going to show any enthalpy gain. So that's why stability is recursive. There's an increasing competition as you grow higher and higher in dimensionality for what is going to be the minimum of the overall the n-dimensional convex hull. And we can get that from the n+1 enthalpy gain. I'll talk more about some of the consequences of that in a later talk. Okay, so I just want to show you that you can do this analysis from your laptop, and you're going to want to download the slides for this talk so you can copy and paste these commands. But you can do this analysis from your computer if you download the AFLOW binary. You can actually run the convex hull analysis using this command here. You run AFLOW, the convex hull. You tell it that you want the convex hull. You specify the alloy system. You can print it out in JSON, text, and PDF format. You can, and there's a number of sort of variants on this query. You can actually directly query a structure's distance from the hull. Okay, so this is going to give you all the results. If you just wanted to return back the distance of a specific entry from the convex hull, you feed in the AUID for that system, and you run DTH. You can get a stability criterion fitting in the AUID. You can also get the energy of the hull at a particular stoichiometry. So remember that the minimum energy surface, the minimum Gibbs free convex polytope, that's defined as the combination or the union of all of these different n-1 dimensional facets, right? All these triangles or all these tie lines. So if I want to know what the energy is at any given point in that composition range, I can also linearly interpolate and figure out what the energy is of that hull, the convex hull at that point, by feeding in the energy of the hull here and providing the stoichiometry where you want to find out what the composition is. Remember that there's implicit coordinates, because if I'm in a binary system, by specifying one coordinate, I want to go to 0.25. I know that the coordinate of the other composition is 0.75 because it has to sum to 1. So you're only going to be providing one less coordinate for that dimension, right? So for a binary, I only need to provide one coordinate. For a ternary, I provide 2, et cetera, et cetera. There are some high throughput inputs here. So if you want to if you want the convex hull to run for multiple systems, you can provide a comma separated list. You can also do this very nice specification, which is actually equivalent to this specification here at the top. I can do MNPT, PDPT here based just on this colon here. I can do colon versus comma. And then I can also do, there's these internal aliases for all of the different combinations of elements that we really run in exhaustively. You can do lib2, and that's gonna generate hundreds of thousands of convex hulls. I wouldn't recommend running that because it's gonna take a long time. Does AFLOW-CHULL work with local data on my computer, or will I have to do an API call? No, as of right now, it has to do the API call. In the future, you may be able to provide, for example, a particular file of compositions and energy, and then it can build the whole. But for right now, it needs to do the API call. Okay, there's also some Python wrappers that we've built, and those wrappers are actually provided in the exercises that we'll be going through in about 5 minutes. So you can see what that Python script is doing, but basically fundamentally it's running AFLOW in the background, and we have the get Hall command, we have the get distance to Hall, we have the get stability, and the get Hall energy. These are basically, these map directly back to these commands that I discussed earlier. You can also create a Jupyter notebook. I'm going to stop sharing the slides because I actually have the Jupyter notebooks takes a bit of time to run on the cluster, but I've run it for you, and you can see here what that looks like. If you open up the Jupyter notebook, you can run it on the cluster. It's perfectly allowed, and you might want to do that for some of the exercises. You can actually run the notebook, and it'll give you a nice plot here. And if you want, you can actually click on this point here. It becomes a point you can click on, and it takes you to the entry page. So you have that for 2 dimensions. You also have it for 3 dimensions here. So you have a whole set of functionality to work at in the Jupyter notebook environment. You can work with it in the Python environment. You can also work with it in the web environment and in the command line. So there's a number of ways, number of different wrappers that we've written that you can interact with the Convex Hall data here. All right, so let's break up for some exercises. I'm going to explain them, and then we'll take 5 minutes we're going to take about 7 minutes to go into our breakout rooms. So if somebody wants to start going through and assigning breakout rooms while I explain the exercises, that would be very helpful. So in the breakout rooms, we're going to do a number of exercises. You can actually do most of these online. And if you want to get a more precise answer for number 3, you can run it with the command line. But the questions are: what is the distance of AL17CO12 from the Convex Hall? You can go to the web, download the PDF, and grab that. You'll do that together in your small groups. What is the stability criterion for Te2ZR? This is something you can also do from the web and the PDF. What is the energy of CuZr at the 0.5 composition? This is something you can actually do on the web if you look by eye what that distance is from the 50-50 concentration to the bottom of the Convex Hall. You can also run the command that you can build the command I showed you earlier for get Hall energy. And then what is the ternary compound with the highest stability criterion? Those are the exercises. So while we're waiting for the breakout rooms to be assigned, I'm going to look at if there's any questions. It looks like we got a few about identifying identical structures. I think I missed it if you talked about it before. So my question is it possible to give two structures to AFLOW as input, get the results if they are identical or not? How? Yes, Dr. Hicks covered this yesterday. You can take any two, really any combination of structures. You can take 600 structures, and you can feed that into the Xtal finder algorithm, and it'll tell you which ones are unique. You can do this based on whether they're unique within a material. So you have to map the species exactly, or you can do a mapping from a prototype perspective, and it'll actually analyze the backbone structures and tell you which are the unique backbone prototypes. So that I refer to the lecture that we did yesterday. That we'll post the videos so you can go back and look at them. What is the meaning of the stability criterion? Is it only energetically? The meaning of the stability criterion is we want to understand. We used it to filter out stable points that are going to be really robustly stable. Okay, because some of these stable points may not be stable when you start to incorporate temperature, pressure. They may not be stable because perhaps we haven't analyzed we definitely haven't analyzed all of the possible phases that exist, all of the hypothetical structures. These convex halls, we're continuously adding data to them. That's why it's important that you do the analysis. The analysis sort of has a timestamp, because there's more and more data that's constantly being incorporated into AFLOW, and that might change the convex Hall analysis. So it's really a measure of assuming that you have very good statistics of your convex Hall, you have a good sampling of the phase space. This tells you how robustly stable the points on the Hall are. Oh, Extel Finder, I'm sorry, we haven't discussed Extel Finder. We really covered symmetry yesterday, but Extel Finder we're going to cover on Friday. Thank you, Dr. Hicks, for clarifying. Okay, so have we built up the breakout rooms? Okay, it looks like the breakout rooms have been built. I'm going to stop sharing and we're going to go into the breakout rooms, and then we'll come back at around 9. Let's come back we can come back in about 7 minutes, 9:43, because I just need about 2 minutes to go through those answers. Okay. Okay, let's give everyone a few seconds to return back. Okay.
Corey?
Yes.
I also got a question in my room whether you can use the CHULL module to basically plot the convex Hall for own user data, so not using the AFLOW data. So maybe you can comment on this question, might be interesting for the general audience.
Someone asked that question earlier. Yeah, the answer is that no, as of right now, we have to make the API call. So you need to use the AFLOW data with the Convex Hall module. However, we will be implementing in future releases of AFLOW the ability to use, you can input, for instance, you can build a special file where you specify the compositions and the energies of the structures, and you can build a Convex Hall based on your input there. But for now, no, we are leveraging data from AFLOW to build the Convex Hall. Let me just send a quick message. Let's come back. Looks like we have 2 rooms. 1 second, I'm going to try to go in and bug them. Okay, let's go ahead. Oh, this looks like we still have 1 room that is still. Can someone jump into Dr. Esther's room and just let them know? MeV of each other. So 4 MeV per atom. So they are duplicates. So picking one over the other is sort of irrelevant. Okay, so for the ALCO question, we want to look this point up in the PDF, and I have it right here. You can see that it's unstable, and its distance from the Hall is 243 MeV per atom. So it's very large. It is very unstable. What is the stability criterion for TE2ZR? I should also have that Hall up. You can see that I have it here, and the stability criterion is 49 MeV per atom. Okay, so you just have to download the PDF, and you can find this information in the PDF here. Next question is about the energy of the CU-ZR Hall. And there's a number of ways you can do it. I actually clicked on the point above the Convex Hall here for the lowest point from the 50-50 concentration. You can see that its enthalpy of formation is 132 MeV per atom, and that its distance from the Hall is 25. So if you want to know what the energy of the Hall is at 0.5, just from this plot, you just take those 2 numbers and add them together. So you're going to get something roughly around a negative 160. I think it's 158 or something like 159. So that is the distance from the Hall from here. You can also build the command here in your cluster. You can actually run this command and it should give you the results. You know, Convex Hall, alloy, Hall energy 0.5, and that's going to return the results for you. Last question is on the MMPDPT plot. And I should have that up somewhere right here. So I asked specifically among the ternaries. So you see that we have one stable composition here. The stability criterion is 33 MeV per atom. We have one more, which has a stability criterion of 1 MeV per atom, and then the rest are binaries and unaries. So the one that has the largest is this Mn2 PDPT. This is actually the composition of the other magnetic system that we found in that Heusler structure study. So you can see here the stability criterion is greater than the 30 MeV per atom threshold that we set. So this is a very robustly stable structure. And I think we have a question here. Mn2, there you go, perfect. Okay, so with that, we conclude today's session. We'll be coming back in about 10 minutes with Dr. Friedrich, who's going to be picking up on the coordination corrected enthalpies. I'll be here. If you have any questions, feel free to unmute or post in the chat, and I'll be happy to answer. It looks like we got a question here, but very quickly, I just want to wrap up and say officially, thank you very much for joining me for this session. I'll put my email address in the chat if you have any questions, and I appreciate your time. Thank you. Okay, so it looks like we have a question here. Can I suggest something when it comes to the CHULL visualization? Maybe it'd be great to color the points with respect to the prototypes. Well, listen, if we color the answer is we cannot, because there are too many prototypes to color. So if we did it based on the prototype, we would have to have different colors for the binaries, different colors for the ternaries. So there's really a lot of different colors we'd have to show. Here we're showing the colors with respect to stoichiometry, because those are really sort of the coarse-grained variables that you can do very easily with different colors. But there are just so many different prototypes in the AFLOW database. You don't have enough color diversity to cover the different prototypes. But it is a great question, a great suggestion, and I appreciate that you made it. Perfect. Thank you. We have over 1,000 different prototypes. These are actually, we actually have a lot more, but these are sort of the official prototypes that are coming from the experimental literature. So this is coming from the prototype encyclopedia that we have. But we actually have a lot of different prototypes that are native to AFLOW that we've been constructing for over a decade now. Okay, well, thank you very much. I will go to mute, and we'll pick it up in a few minutes with the next talk. Thank you.